Ooh, I went for 34 today. 3 more to go. Yes. All right, so we started recording. Pay attention to the light. Last time we talked about error correction, error detection stuff, and then where we stopped off was when we talked about cyclic redundancy checks. We said they were powerful. We said they were better than 2D parity because they allow you to correct burst errors, right? Which is when you get a whole bunch of bits that are in error and they're all bunched up together, right? And where we stopped off was doing an example calculation, and we talked about the importance of the generator polynomial and how the generator polynomial needs to be a primitive polynomial, and how that guarantees the ability to check R burst length errors. And so we went through a calculation, and the last thing I wrote, maybe before the recording got busted, was that after you calculate the remainder, what you end up doing is inserting that into your data portion, and this is what you send across to your receiver. And once the receiver gets his data, all the receiver has to do is now, this particular number here, we know is a multiple of G, right? Because we made it so, right? Yeah. So all the receiver has to do is to essentially, to check, is to take this portion here, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, hopefully I didn't make a mistake, and divide that by our generator, which is 1, 1, 0, 1. And if everything goes well, somebody said after the lecture recording was over, what you should get is a 0, that's right. But if there's an error, you wouldn't get a 0, right? Because that means this number is now divisible by that number, right? And there's no remainder, okay? We made it so, right? That's the idea. So do you have any questions on that stuff? So that pretty much concludes all the stuff we're going to talk about in terms of error correction and error detection. The next thing we want to talk about in terms of the data link layer is multiplexing. So you've seen a little bit about multiplexing before. So multiplexing is a process of combining multiple signals, right, over a shared medium, right? Could be a wire, could be air, whatever it is, right? Multiple signals. How do we send multiple signals down a shared medium? That's what multiplexing is about. And it turns out the link layer has to deal with this problem because often there are shared mediums over which data is sent, like a piece of wire or air, like now, okay? Especially with Wi-Fi and stuff, right? So how do we do that? So there's a whole bunch of ways we do that, and it's called access protocols, right? Okay, access protocols. What are access protocols? They just defining some rules about how you share a channel, right? How you do multiplexing. And these access protocols have to be implemented at the data link layer, right? Somewhere, okay? Maybe as software, maybe as hardware. So we're going to look at is a whole bunch of access protocols that are out there for doing multiplexing, right, over a shared medium, okay? Just to give you a kind of a motivating example, or just a bit more background. Typically, we have some links which are, point to point. In which case, if you're a data link layer talking from your modem at home to your ISP, you could say if it's a phone line and 56 kilobits per second modem, no one else is using that line, right? It's a point to point link. It's yours. So you don't need to really have multiple access protocols for that, right? So we do have point-to-point links. We used to look at PPP. I think it's still part of the course. So some links are point-to-point, where you don't really have a concept of a shared access. But some links are broadcast. Examples are Ethernet cables, or even Wi-Fi is a good example. So here's an old example, right? This is a bit old school in the sense that Ethernet networks used to look like that. There was a big wire, and everybody was connected to that wire, right? So that means all these stations needed to figure out how to share this wire. If you transmit at the same time, it's the same effect as you and me talking at the same time and nobody being able to understand what's being said. Okay, but you may not find these networks anymore, because typically Ethernet networks are now connected over a switch, and like that. So the switch takes care of, which we'll look at later. Basically, the switch puts each of these stations into a separate collision domain, so there are no collisions anymore, right? But this is what it used to look like, but this is what it looks like now. So this used to be called a tree topology, and this is called a star topology. Oops. Star topology. But you're familiar with this Wi-Fi, which you use now. So everybody has to share a frequency channel bandwidth, right? And everyone's transmitting on that. How do we share that airspace between multiple users? Satellite links. The analogy is, of course, you turning up to a party and everyone's talking, no one can understand what's going on. Or maybe you have a video conference. There's 50 users at the video conference, right? Everybody wants to discuss something. How do you do it? How do you go about doing that? Same kind of problem is what we have to solve, right? In terms of looking at multiple access protocols, typically what you want to pay attention to, or what I'd be looking to see if you understand or have an appreciation for this stuff. Is it fair? So fairness means, is everybody getting a fair turn at transmitting, right? Or there's someone being starved, okay, right? That's fairness. Efficiency. What happens if you increase the number of nodes on a network, right? How efficiently can we use the bandwidth? We have 1 gigabit per second link, and if you put 100 users on that, it turns out that we're only able to use 20% of the bandwidth, right? So we're paying for 1 gigabit links, but we're only using 20% of that, right? So it's not a very good use of that shared medium, right? Because there's all this excess capacity not being used. So how efficient is your multiple access protocol, right? How much of the available bandwidth can a user use? If I have 1 gigabit to send and no one else has any data to send, why shouldn't I be allowed to use the whole bandwidth, right? Okay, so efficiency. Complexity is really about, so at the end of the day, you can come up with the funkiest protocol in the world, but you got to implement it, right? So it's got to be implemented in software or hardware, right? Right? It might require coordination, timing, blah, 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 right? How do you get all this stuff? And doing that may not be so simple. So there's a cost to pay, right, in terms of hardware and performance. So what is the complexity of the protocol? Is it decentralized or centralized? So this is quite classic. If it's centralized, that means you have a single point of failure. If it's decentralized, that means you can have nodes come in and go as you like, and the network should survive. It's dynamic, right? So these are some of the attributes you want to pay attention to in terms of looking at different solutions for doing multiplexing, right? Keep it simple. We're going to look at three, kind of bunched up into 3 different categories, if you like. So the first one is called channel partitioning, right? So this idea is quite straightforward and simple. A second class of multiple access protocols are called random access, right? And the third one's called taking turns, okay? This idea is extremely simple. Let me hold on to that for a minute. So one is, if you think of Wi-Fi, or if you think of some frequency, then one way to divide up a shared medium is by dividing it in terms of frequency bands, right? So let's say you have a spectrum, 200 megahertz, and maybe you can divide it between n users and say, you can have 10, you can have 10, you can have 10, you can have 10, right? You can have 5 hertz, 5 megahertz, whatever it is, right? So one idea is to allocate different frequencies for different users, right? Oh, wrong class. So that's one way to do it, right? So maybe we have, so this user has F1, this user uses F2, maybe this user uses F3, etc. So each user has a different frequency channel that they talk over. But unfortunately, that means that if this is the only user that has data to transmit, then that means all these other users are idle, right? But the available bandwidth for this user is, 1 over n, right, of the total bandwidth, right? So that means I can't use these frequencies down here, yeah. Okay, so even though they may not be used by anyone else, right? So if you have frequency division where you have channel allocations, like in Wi-Fi, you have 12 channels out here. So and you can occupy a single channel, but why can't I use the other channels, right? If I have a lot of data to send. So you're always going to be limited by the number of channels that you split the shared medium into, right? So that's your total bandwidth that's available. So that's called frequency division multiple access, right? Typically you'll find Wi-Fi uses frequency division multiple access. Then there's some classic, so GSM is a good example of this one. And who has a GSM phone these days? No one. GPRS, GPRS, and Edge, EDGE. I need to improve my handwriting. So the idea here is with GSM is, so you have slots, and a slot is divided into a fixed time at something like 200, 300 microseconds, and each slot you have fixed time intervals, and you allocate one time interval to a user, right? So this is user 1, this is user 2, this is user 3, user 4, user 5, user 6, and then the slot repeats again. So you're only allowed to transmit during this time period, right, for user 1. And user 2 obviously has nothing to send, so it's empty. User 3 has something to send. 4 has something to send. So the next time you're allowed to transmit is after this slot interval, right? So whatever this time interval is. Okay, and then the next time you're allowed to transmit is after that slot time interval. So in GSM, essentially, this would be one mobile phone user to another mobile phone user, another mobile phone user, another mobile phone user, right? And another mobile phone user, and another mobile phone user. So you have the same problem as before, right? So in this case, there's 1, 2, 3 empty slots, but I may have a lot of data to send, but I can't use them, right? So the available bandwidth, if you like, is still 1 over n, yeah, to a single user, okay? Even if no one has nothing to send, right? So in terms of fairness, okay, it's pretty good. Everybody gets a turn. FDMA, frequency division multiplexing. I have my own channel, everyone else has their channel, so it's fair. And I want to send, I can send. But in terms of how the channel is utilized, it's not so good, right? Okay, because if no one has anything to send, I can only send in my slot, and I can't use any of the other slots that are allocated to someone else. Okay, so bandwidth is still 1 over n, because n is the, let's say, number of users, right? So available bandwidth to you is still a fraction, right, determined by the number of users that you're trying to put on here. So that's channel partitioning, using frequency and time. So there's another way to partition a channel, which is using codes. So which is basically, these days, 4G networks use a combination of frequency, time, and code, right? Use everything. So code division multiple access, the idea is that all these other two methods, your total available bandwidth is always going to be 1 over n being the number of users, right, that you divided among. So the idea with code division multiplexers is say, well, you can use the whole bandwidth, right? Everyone can have the whole bandwidth. You got something to send, just use the entire bandwidth, right? 200 megahertz spectrum, so that's a lot of data you can send in one go, right? And so that was the idea. But then you have a problem. So if everyone talks at the same time, they're all going to get jumbled up, right? Turns into noise. So you can't decode it. But there's a cool way to do that, which is using what's called orthogonal codes, right? So it turns out that if you take your signal and multiply it by one of these orthogonal codes, orthogonal means that two codes are at 90 degrees to each other, right? So, so if you take a dot product, that's 0. So if you multiply by one of these orthogonal codes, which is called a chipping sequence, and everyone has a unique code, which is at 90 degrees to every other code everyone else uses, then it turns out that you can recover the original signal, right? So there is a slide, but there's a very short animation, very short one. Maybe you can just look at that. It may have some really like crappy music, I'm not sure. So remember the idea is you take your data, you multiply by a chipping code, and this chipping code has a special property. That is, every chipping code is orthogonal to every other chipping code, right? So if you can come up with such a chipping code, we're done. That means we can put all these signals into the same space and still be able to recover them individually, right? So in this case, this is one orthogonal code, and this is another one, right? So these two codes are orthogonal because if you multiply them together, right, you get essentially 0. So imagine this is his chipping code and this is someone else's chipping code, right? Two orthogonal codes. So orthogonal in the sense means that if you multiply them, you should get 0. Multiply and add. So minus 1, 1, minus 1, minus 1, and you add them together, you get a 0. So every code that you have is orthogonal to every other code, right? It's pretty cool. And have you heard of Welsh codes? Welsh? So that, you've heard of Welsh codes. So, so that's what pretty much chipping codes are based on, right? So there's actually a nice formula for coming up with, so long orthogonal codes, right? So imagine that two people now have two orthogonal codes, and in this case you have here's your chipping sequence, in other words your orthogonal code. So in this case you have a sender and a receiver, so the receiver also needs to know the same orthogonal code, so this one over here, 101101, 101101, and what? Chipping sequence and chipping sequence? It's a bit confusing. One of them should be data. I think it's an error. Oh, okay, yeah, sure. This is, so chipping sequence 0 is a -1 and 0 is a -1. So you can't, 0 is represented as a -1, okay? Sorry. So if you want to send is this animation? Did we skip something? What happened? So you want to send a 0. So you want to send the data bit 0. 0 is represented as a -1. So what you do is you take that data bit and multiply by your chipping sequence, okay? Right? So 0 is represented as a -1, and then you multiply by your chipping sequence, in which case you end up with 1, -1, 1, 1, -1, 1. And then at the receiver, you multiply by the chipping sequence to recover the data bit, right? So that's just multiplying the received value with your chipping sequence. And then you sum it up. And if the sum is less than 0, then it's a 0. But if the sum is more than 0, then it's a 1, right? That's how you recover it, okay? So that's essentially the process that CDMA follows. Now to do that again. Now to do that again on the lecture slide. So the idea with CDMA is actually, so you're not using frequency to divide up people, onto the shared medium. You're not using time to divide up people onto the shared medium. You're actually using a special orthogonal code to divide up people into the shared medium, right? So exactly what happened before is, so here's the orthogonal code, right? And then here's the data bit you want to send. So remember, 0 is represented as a -1, okay? So what you do is you actually, so you want to send the data bit 0 and 1. 0 is encoded as a -1, and you multiply the two together, just as in the animation, and you end up with this sequence, right? This is what you transmit onto the channel. And then when you want to recover it, just as in the animation, what you do is you take your orthogonal code, and then you multiply it with the received signal, right? So in this case, if you multiply, you have -1, which is 1, 1, 1, right? And then this is a 1, so that 1, 2, 3, 4, 5, 6, 7, 8, right? So you got the value 8 here. So this is greater than 0. This implies it's a 1, right? Okay. And again, if you do the same multiplication here, so yeah, this is a -1, so that's a 2, 3. I'm adding up as I'm going. So that's, sorry, this is -1, -2, -3, -4, -5, -6, -7, -8. So 8. So this is less than 0. This implies it's a 0, right? Okay. So if you multiply with the orthogonal code, it turns out you can actually recover the data. What's really cool, what's really, really cool is that it's a bit like saying all this data exists in the same space, same time and frequency, but in a different code space, right? Yeah. So, and these code spaces are all orthogonal to each other, right? So, and I can pick and choose the one that I want, if you like. I can pick that one if that's mine, or pick that one, or pick that one, right? And that's what the chipping code is doing, right? It's kind of picking out. So if you go home today, and if you're really keen and interested, you could try that. So here we have two different chipping codes, right? So this is code 1, and this is code 2, right? And here's a 1 and a 0 being sent, and here's a 1 and a 1 being sent. So essentially what happens in real life is that this will get multiplied by this chipping code, this will get multiplied by this chipping code, and then what gets transmitted will be superpositioned in time and frequency, right? So what gets sent is something that's superpositioned in time and frequency, so which will end up looking something like that, right? But the really cool part is that now this actually has information from two senders, right? It doesn't look like it. It looks really messy and ugly, right? Somehow these 2 bits, these 4 bits of information are here, right? And if I want to recover sender 1's information, right, all I need to do is to multiply whatever I received by sender 1's chipping code, and you'll get back the right answer. And we can see that quite quickly, because here is 0, 0, so that's a positive 2. -2 into -1 is positive 2. That's another 2. That's a 4. I'm adding as I'm going along, right? And that's another 2, 6, and 7, 8, right? So this has a sum of 8, which is greater than 0, which implies it's a 1, right? Okay, so it's beautiful, right? It's like magic. So having these codes and being able to transform your signal into orthogonal code spaces, right, allows you to use the entire bandwidth at the same time, each user. It's not so perfect like that, because if you increase the number of users, you do increase the noise in the channel. That means it does become a little bit harder to recover, so that's why you may find that as in a 3G or 4G network, as the number of users increase, you will find that your data rates will also reduce, because the amount of kind of noise that's in the channel also increases, right? But theoretically, it's pretty cool, because if no one is using the channel, you got the entire channel to yourself, right? However much bandwidth you want, it's to yourself, right? Which is something that TDMA and FDMA couldn't do, right? Was that exciting? No? You already knew that? That's good. All right, so we got TDMA, time division multiplexes. We got frequency division multiplexes. then we can also divide using codes, orthogonal codes, using code division multiplexers. Right, if you want to find these codes, look for Welsh codes, or read up on the Hadamard matrix, which is a way of coming up with orthogonal codes. So the second stuff I wanted to talk to you about was random access, right? So one way is to have these strict divisions. Think about these partitioning. These partitions are hard, especially time. So if you want to do time partitioning, what do you need to have between sender and receivers? What do they need to have? You want to have these strict time intervals. What's the cost of doing that in GSM? Remember? What did GSM phones need? Really accurate? Really accurate what? Come on. It's time division. What do you need? Really accurate? Clocks. And all the phones need to be synchronized, right? Because I need to know when the slot starts and slot finishes, because if I don't do that, it's going to be a collision, right? So everything needs to be synchronized. That's not an easy task, right? You need to have all devices synchronized so everybody knows the start and ending times of slots. So there's a price to pay, right? That's pretty complex to implement. That's not easy, right? Having all the phones and devices synchronized to a single clock, knowing when slot starts and slot ends, and this is being measured down to microsecond level, not milliseconds, microseconds, right? So there is a cost to pay. There's a complexity involved in being able to do this stuff. So random access is nice. Just the idea is simple. You want to send something, just send it. Don't wait around, right? So all the random access protocols are around when a node has a packet to send, transmit at full channel data rate. Okay. So there's no prior coordination. There's no frequency. There's no codes. There's no timing, right? No prior synchronization. But the problem with this approach is it's nice because typically not everyone may have data to send exactly at the same time, right? So statistical multiplexing gains, right? Okay. So that means typically random access should work okay, unless it's like 5 o'clock or 6 o'clock peak hour traffic time, right? I'm talking about buses and roads, but if you think of a data channel as a road. But the problem is you're going to end up with collisions. That is two people talking at the same time. So all the random access protocols are really about trying to deal with this problem, right? And can you deal with this problem well and efficiently? Because if you can, then perfect. You've got a beautiful solution, right? No prior coordination required. Everyone at random can transmit when they like. Full channel data rate, right? Problem is this guy. So how do we deal with this problem? Collisions. That's what most of the random access protocols are about, okay? First, you need to detect, one way is to detect collisions, and then when there's a collision, you go abort, stop, try again. And the other one is avoid collisions, right? Try to avoid collisions from happening in the first place. So examples of random access protocols we're going to look at are especially slotted aloha. It's a classic protocol. Every computer network student should know this one, I guess. Then there's also carrier sense multiple access and carrier sense multiple access with collision detection. I think we're not going to look at this one anymore. So we're going to look at these guys, okay? Slotted aloha, and carrier sense multiple access with collision detection, right? Okay. Let me hold on to that. So let's take a look at aloha. How does this guy work? So aloha, it's not an acronym. I always thought it was an acronym. Turns out that they came up with it in Hawaii, so they called it aloha. So just a side note. So although it's written in capitals. So the idea with aloha is that slotted aloha, pardon me. So there's two versions. The original one is aloha, but this is slotted aloha. The idea with slotted aloha is time is divided into equal size slots. So basically, a slot is packet transmit time, right? So I don't know, 1,500 bytes. How long does it take to transmit it down 1 gigabit per second link? That becomes the size of a slot. Okay, and the idea is that node with new arriving packet transmit at the beginning of next slot. So here in this example we have 3 nodes, 1, 2, 3, and then let's say all 3 nodes get a packet to send just before this slot. So if a packet arrives and I have something to send, you just send it, random access, right? So all 3 of them transmit at the same time. But unfortunately, what happens here is a collision, right? It's the same as 2 people talking at the same time. So you have 2 electrical signals, 3 electrical signals being put onto a wire, if you like, or radiation coming out of 3 receivers at the same time into the same channel, right? Just ends up being noise, okay? So the idea is that if there's a collision and it fails, so you retransmit the packet, right, in a future slot with some probability p. So if you like, you can think that each of these nodes after a collision, rolls a die, right, and then this guy may get maybe this guy gets 2, maybe this guy gets also 2, maybe this guy gets 1, 2, 3, 4, 5. Okay, let's say, right, 5, 2, 2, and then so there's 3 random numbers, and what I do is I count them down for each slot, right? So 2 minus 1 is 1, then in the next slot it'll be 0. So I go, yep, I transmit. This guy also happened to pick the same random number, so ends up transmitting in that slot. Oh, this guy picked 5, so it's 4, 3, 2, 1, 0. He transmits here, so he doesn't collide. But these 2 nodes just happen to pick 2 random numbers that are the same and ends up transmitting at the same slot, and we have another collision, right? Okay. So what do they have to do? Do this again, right? Pick a random number, right? Wait a random interval of time and transmit again, right? Try again, right? So that's the nature of random access protocols, right? Okay. And eventually, so happens that these 2 decided randomly to transmit at the same slot, and there was a collision, right? So that means, but this was successful, so it's a successful slot. And again, pick a random interval and decide when to transmit. So that's the idea with slotted LOR, right? So this is kind of pretty cool because there's no, coordinating body. I have something to send, I just send. If it collides, I just take a break, random time, and try again. And just keep trying and keep trying. Okay, so you've gotten rid of most of the coordination stuff, and so it's pretty decentralized. But the trouble is that now we have to deal with collisions. Okay. So if you just think about this small picture, you'll see that how many slots are wasted, right? Can you see the number of slots wasted? When do we have a wasted slot? When we have a sorry? E is empty. So we got an empty slot, that's wasted. And when do we have a wasted slot? When we have a collision, right? So if you really think about it, it's pretty crappy, right? It's so we got a lot of bandwidth, there's can't really use it. Right? That's just the typical nature of a random access protocol. Lots of empty slots or lots of collision slots, right? And you'll see that as we do the next exercise. So I gave you guys something, right? So what we're going to do is the class is try and calculate the efficiency of slotted LOR. It's fun. we should do a little bit of maths, right? Huh? Did you get one? Yeah, I've got some shit. Have you guys all got one? I have a few more. I expected 34. I've got 32 students. Oh, yes. 33 students. Yes. I'm perfect. See, I should be an engineer, right? Good at estimating. Oh, I am one. So what I want to try to do is to at least give you some sense of, take a classic protocol like slotted LOR, and then try to see how we go about calculating the efficiency, right? So let's assume that there are n stations. So in other words, means there are n nodes, if you like, that want to send packets, and each node is going to transmit I mean, we have to make some assumptions, right? I mean, you can't, otherwise it's going to be impossible to do this calculation, right? So we're going to make some assumptions. So we assume that each node wants to transmit with some probability p, right? So any given node will transmit a probability p. Then probably that a given node has success in a slot. So if there are n nodes and I want to have a successful transmission, that means I should be the only one transmitting, right? And every other node shouldn't be transmitting, right? So that probability is going to be equal to me transmitting and every other node, which is n minus 1 nodes, not transmitting, right? Okay, so I have a successful transmission, and all other nodes are not transmitting. So that's the probability that I will have a successful transmission, right? But what's the probability that any of the n nodes will have a successful transmission? So that means this one, right, is this probability of successful transmission for a single node. For n nodes, it'll be this plus this plus this plus this plus this n times, right? So it's going to be n times p into 1 minus p n minus 1, right? So this is like a binomial distribution. Probability of success for an experiment is p. Failure is 1 minus p, right? Okay? So that's fairly simple. So we have now a way of determining a probability for any given node to be successful, right? But what we want to find for max efficiency is actually what we want to do is to find a value for p. What's a value for p? That means the probability that I can transmit that maximizes so what value of p can make probably that any node can successfully transmit a packet maximum, right? Okay, what value of p will make this guy the maximum, right? So this will give us a value for p that says that if my transmit probability is this value, then the chance that any node will have a successful transmission in a given slot is high, right? Because we don't want to waste any slots, right? We want to make sure that at least one node has a successful transmission in the slot, okay? How can we maximize this chance? That's what we're trying to do. So this is kind of like high school maths for you, because we can now express efficiency as a function of p, which is the probability of a transmit, as being equal to np 1 minus p n minus 1, right? So if you want to determine the maximum of a function, what do you guys do? Huh? High school maths. Yeah, that's right. You differentiate. You find where the derivative is equal to 0, right? It's yeah, it's so easy. So that means if this is my formula for efficiency as a function of p, then if I want to find where this takes the maximum value, I differentiate this and find where the derivative equals 0. So it's a little bit tricky, but I make a lost. So this is a product thing, right? So we end up with n into 1 minus p n minus 1 plus np, differentiate what's in the brackets, 1 minus p, just write it out, n minus 2, n minus 1, and just the minus 1 from p. So simplify things a little bit, n into 1 minus p n minus 1 minus np1 minus p n minus 2 n minus 1. So it's helpful, but it's not helpful for us to set to find when the derivative is equal to 0. So I'm need to factorize this thing into something a little bit more useful. So here's a tricky part. N minus 2 1 minus p n minus 1. Now, if I want to set equal to 0, so this is a trivial solution, right? So let's use this. So essentially, I should end up with 1 minus p is equal to p n minus 1. So 1 is equal to np. I'm just writing because I know the answer. So p. So the value of p, which actually maximizes the probability that any node has a success, is 1 over n, right? If a node's probability of it kind of makes sense, right? If a probability, that makes sense, yeah? It almost feels intuitively correct. So if you have n nodes and the probability that I will transmit is 1 over n, then that is the only time at which we can make sure that the probability of any node being successful in a given slot is maximum, right? But we don't care about one node. We want to know what happens when we put a whole bunch of nodes, right? We want hundreds and thousands of nodes. What is the channel efficiency? You can't calculate the efficiency for one node, right? What happens when n becomes really large? Okay, we connect lots of hosts together. So, so what we want to do is this guy, right? So, okay, what happens as we increase n, okay? So we know that this probability is now equal to, whereas here, so it's n into 1 over n into 1 minus 1 over n into n minus 1, right? So we can just substitute this probability back in to calculate the peak, the highest maximum success. And this ends up being 1 minus 1 over n minus 1. This goes off. So the way we do n becoming large in maths is to take limits, right? So in the limit up as n tends to infinity, so this is not very helpful in terms of calculating limits. You can use L'Hopital's rules or whatever, but we can rewrite this as 1 minus 1 over n to the power n over 1 minus 1 over n. Now this is a little bit more helpful. So because the limit that n goes to infinity for this one is just 1, and for this guy, it's known, right? It's a known result. It's actually equal to 1 over e. So this result is 1 over e, okay? So it turns out that e p star is actually equal to 1 over e as n becomes really large, okay? Who knows the value of e? It's natural log. Anyone? 1 over e? Turns out it's like something like 37%, okay? So roughly around 37%. Right? That's pretty low, right? Okay? So that's a probability of any node being successful in a given slot. That's pretty low. But that's the price to pay for decentralized. No control, right? So this is your slide, which is in your books, I guess. So it turns out that at best, the channel used for useful transmission is only 30% of the time, right? So majority of the time, what's happening? What's happening? Huh? Wasted slots, empty slots. What's the other thing? Collisions, right? Majority of the time, you have empty slots and collisions. That's what happens, right? Clearly, if you increase n to be large, most of them are going to be collision slots, right? Okay? So that's what's happening. Only useful amount of time that you transmit is actually only 37% of the time. So, by the way, slotted aloha is still used, right? I mean, you know, I work in RFID. That the protocol that it's based on is slotted aloha, right? It's simple because it's simple, right? It's very simple to implement, and that's an advantage, right? Because that means the hardware cost is low, right? So, good but bad. But here's pure slotted aloha. Things get a little bit worse for pure slotted aloha. So in the pure aloha, which is there's no slots, the idea is you know, there's this synchronization part in terms of having slots is gone. But so instead, when you have something, but you have a defined packet size, you know, could be Ethernet frame size, whatever it is. So the idea is that when you have something to send, you just send it, right? Clearly, this will increase the collision probability. So the example here is that you don't wait for a beginning of a slot, right? You just, when you got something, you send it, right? So this translates into increasing collision probability. And you can see that here. So assume that at t equals 0, this node has a packet to send. And so it's transmitting this packet onto the link, transmission time, right? And at so it takes 1 time unit to transmit, right? 1 time unit to transmit, okay? So when it starts, another node here has already sent a packet, but hasn't really arrived here. Why? May not have arrived here. Why? Or may have arrived here. We don't know. But may not have arrived. It wouldn't have arrived because of what delay? Propagation delay, right? Okay. So the fact that when I'm transmitting here, it could be that a packet that was sent previously arrives and collides. It may be that another person who decides to transmit before I finish putting my packet on the link also collides, right? So maybe I didn't do that too well. So I guess the idea is that I have a packet to send, and when I have something to send, I just send it, right? But I technically increase my collision probability because none of these other senders are waiting for their slot time. They just send, right? So you almost double your collision probability, right? Because the other people are not waiting for you. And this stuff that is still being transmitted, transmission time, propagation delay, transmission time, propagation delay, transmission, propagation, all this stuff, we're just going to collide with each other, right, at the end. So the fact that these guys are not waiting for their slots and can transmit anytime means you effectively end up doubling, right, your collision probability, right? So if you look at the way to calculate pure aloha's efficiency, so for you to be successful now, you'll see that here, is that you want to make sure that probably that your node transmits. So this is your node, if you like. And you want to make sure that no other node transmits in 1 unit time before you, right? Because you still haven't finished. There's a transmission delay for you to put the data onto the network and for the data to travel. And no other node also transmit in the next, if you like, until you've finished, right, sending your data, right? Okay? So you want to make sure nothing is sent before or after you, right? Okay? Because the reason is that no data, when you if you go back to this this example, basically what you want to make sure is that no other node transmits here or here, right, for you to be successful. Okay? So if you do this, then it turns out efficiency is now about 18%, right? Half of what you had before, okay? And if you want to, so this graph is kind of interesting. Remember that we calculated the value of P for which